Have you ever wondered what makes an airplane fly? There are four forces acting on an airplane in flight. These forces are lift, weight, thrust, and drag. The study of these forces and their role in flight is known as aerodynamics. In this section, we will discuss how these forces work together to achieve straight and level, unaccelerated flight. This means that the airplane isn't turning, climbing, descending, or changing airspeed. It should be fairly clear that before an airplane can fly, lift must be created. Lift is the upward force created by the effect of airflow as it passes around the wings. Weight is the force that opposes lift and is caused by the downward pull of gravity. Thrust, created by the power plant, propels the airplane forward through the air, while drag opposes thrust. If both of these forces remain equal, the airplane will not speed up or slow down. Before we get into the principle that explains how lift is created, let's look at some of the terminology used in this section. A line drawn from the leading edge to the trailing edge of an airfoil is referred to as the chord line. The camber of an airfoil is the curve of its surface. On general aviation training aircraft, the upper camber is usually more pronounced than the lower camber. Any object moving through the air encounters a relative wind. This wind is always parallel to and opposite the flight path. The angle formed between the relative wind and the chord line is called the angle of attack. The principle behind lift was discovered by a Swiss physicist named Bernoulli when he observed what happened to air as it passed through a tube. The principle simply states that as the velocity of a fluid or gas increases, its pressure decreases. He also found that with a constant velocity, the pressure of the air remains the same at both ends of the tube. If a constriction is placed in the middle of the tube, the same amount of air has to go through a smaller area. This increases the velocity and decreases the pressure. If you were to replace the constriction with an airfoil, such as a wing, the same principle would still apply. As oncoming air meets at the leading edge of the airfoil, it separates with part of the airflow going over the top and part going below. Since the air flowing over the top has farther to go, it must travel faster. The result is lower air pressure above the wing. Because higher pressure tends to flow toward areas of lower pressure, the airfoil or wing is lifted. This accounts for about 75% of lift. The remaining lift is provided by the downward deflection of air as it strikes the bottom of the wing. This can be explained by Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. The reaction to the air striking the bottom of the wing is an upward or lifting force. The amount of lift that a wing can produce depends on several factors. One of these factors is wing design, which includes the shape or plan form of the wing. A straight wing has good slow flight characteristics, but is not structurally efficient in terms of lift and drag. A swept back or delta wing is much better at higher speeds. The tapered wing, on the other hand, has good slow flight characteristics and has a relatively efficient design. Another wing design factor is the aspect ratio, or the relationship between the wing's length and width. The aspect ratio can be found by dividing the wingspan by the average chord. In this example, the wing has an aspect ratio of 9. At a given angle of attack, the larger the aspect ratio, the less drag produced for the same amount of lift. General aviation training aircraft, for instance, normally have aspect ratios of 7 to 9, while gliders are usually between 20 and 30. You as a pilot can control lift by changing individually or in combination the airplane's airspeed, its angle of attack, and the wing configuration, such as lowering the flaps. If all other factors remain constant, doubling an airplane's airspeed develops 4 times more lift. This increase, however, is not without its drawbacks, because along with any increase in lift, you also get an increase in drag. In addition, with all other factors remaining constant, an increase in angle of attack increases lift. For lift to remain constant, airspeed and angle of attack must be used in conjunction with each other. If airspeed increases, you must decrease angle of attack. Conversely, if you want to maintain the same amount of lift at a slower airspeed, you must increase the angle of attack. However, angle of attack can only be increased so far. For every wing, there is a specific angle of attack where the maximum amount of lift is obtained. This point is called CL max, or the maximum coefficient of lift. Beyond this point, the airflow will not remain smooth over the wing, as shown by this water tank demonstration. It becomes so turbulent that the airfoil can no longer create lift. At this point, the wing is in a stalled condition. In order for the wing to fly again, the angle of attack must be reduced. When the wing is below the critical angle of attack, the airflow smooths out and the wing produces lift again. It should be noted that an airplane stalls whenever the critical angle of attack is exceeded, which can occur in any flight attitude and at any airspeed. The third way of controlling lift is by changing the configuration of the wing. Lowering the flaps can increase the lifting efficiency of the wing and decrease the airspeed at which the airplane stalls. As flaps extend, they change both the camber and the chord line of the wing in the area of the flaps. This not only produces the lower pressure above the wing due to the change of camber, but it also changes the wing's angle of attack. Suppose that with the flaps up, the angle of attack is 5 degrees. By lowering the flaps, which changes the chord line, the angle of attack has increased to 10 degrees. This higher angle of attack provides more lift and more drag. The thrust necessary to overcome drag and propel the airplane through the air is produced by the power plant. If you look closely at a propeller, you will notice that it looks like a twisted airfoil. As the propeller turns, a lower pressure area is created in front of each rotating blade. This provides the thrust which moves the airplane forward. The force acting in the opposite direction to thrust is drag. There are 2 types of drag: parasite and induced. Parasite drag includes all the drag not directly related to the production of lift. It is generated by those areas of the airplane which disrupt the otherwise streamlined flow of air. This includes parts protruding into the airflow, such as the landing gear, rough surfaces, and the mixing of the air, such as where the wing and fuselage meet. As the speed of an airplane increases, the effects of parasite drag also increase. In contrast, induced drag is a direct byproduct of lift. It is greatest at slow speeds with a high angle of attack. Conversely, at higher speeds and at a lower angle of attack, induced drag decreases. If the 2 drag curves are combined and the values added together, there is a point where drag is at a minimum. This point is known as L over D max, which is where lift, when compared to drag, is at its greatest. In later sections, you will see that flying the airplane at this speed provides the best glide ratio and other performance benefits. The information presented in this section has provided you with a fundamental knowledge of the forces at work on the airplane during straight and level, unaccelerated flight. The next section will expand your knowledge of what happens to the 4 basic forces during maneuvering flight.
to yaw to the right. Keep in mind that in flight, the rudder is not used to turn an airplane. Its primary function is to align the fuselage with the direction of flight. The three axes just discussed all intersect at the balance point of the airplane, called the center of gravity, or CG. Your airplane pitches, rolls, and yaws about this point. In addition, the entire weight of the airplane can be thought of as being concentrated at the CG. To better understand how an airplane turns, it helps to visualize the forces involved. We can relate turning flight to race cars being driven on an unbanked track. Moving objects tend to travel in a straight line unless something acts on them to create a turn. This turning force is called centripetal, or center-seeking force. In a race car, this force is provided by the friction of the tires and the road. The force that acts opposite to the turn is referred to as centrifugal force. If the tires don't provide sufficient traction, the car will skid to the outside of the turn. Similarly, to turn an airplane, you must create a centripetal force by initiating a bank. As you enter a turn from straight and level flight at a constant airspeed, lift is the only one of the four basic forces that changes. Banking the airplane inclines the direction of lift so that it not only acts vertically, but also has a horizontal component. The combination of these two components is the total lift produced by the wings. Because of the turn, the vertical component of lift is reduced. This means that in order to maintain altitude, you must increase lift by increasing back pressure and therefore the angle of attack until the vertical component of lift equals weight. The horizontal component of lift, or centripetal force, causes the airplane to turn. As in the example of the race car, it is opposed by centrifugal force. In a steady-state turn, centripetal and centrifugal forces are balanced. The resultant of weight and centrifugal force is the load that the wings must support. It can be expressed as load factor, or G's, and is the ratio of the load supported by the wings to the actual weight of the airplane and its contents. In straight and level flight, the wings must only produce the lift necessary to offset gravity. Therefore, load factor is expressed as 1G, or 1 times the force of gravity. As mentioned earlier, when you enter a turn, the wings must support the weight of the aircraft and produce the lift necessary to turn the airplane. By the time you reach 60 degrees of bank, the additional lift has increased to twice the weight of the airplane, or 2 Gs. As the bank angle gets steeper, the load factor increases dramatically. An increase in bank also increases the stalling speed of the airplane. This graph shows that at bank angles less than 45 degrees, the stall speed gradually increases. At steeper bank angles, the stall speed increases significantly. In addition to causing an increase in stall speed, excessive load factors can overstress airplane components. By observing the operating limits contained in the pilot's operating handbook, you can help ensure that the airplane is operated within safe parameters. You will recall that when you deflect the ailerons to bank the airplane, roll is produced by the unbalanced production of lift. The wing with the down aileron produces more lift than the wing with the up aileron. The wing producing the increased lift is also producing increased drag, which is always the byproduct of lift. Since one wing is producing more drag than the other, a yawing force is created, causing the airplane's nose to move towards the outside of the turn. This is called adverse yaw. You overcome this yawing tendency by applying rudder in the direction of roll as you enter a turn. Once you've established the bank and the ailerons are neutral, rudder pressure is no longer necessary. When you move the ailerons in the opposite direction to roll out of the turn, you must again apply rudder in the direction of the roll. So far, our discussion of turns has concentrated on those turns initiated by you. However, propeller-driven airplanes have several left-turning tendencies which you will have to compensate for during various phases of flight. One of these is torque, which is simply Newton's third law of motion at work. For every action, there is an equal and opposite reaction. The force required to spin a propeller clockwise, as viewed from the cockpit, acts on the rest of the airframe as a force in the opposite direction. In other words, the airframe tries to rotate counterclockwise or to the left, about its longitudinal axis. Another left-turning tendency caused by the propeller is P factor, and is most pronounced at high angles of attack. When the propeller's plane of rotation is perpendicular to the relative wind, the ascending and descending propeller blades have equal angles of attack. If you rotate the airplane to a nose-high attitude without changing the relative wind, the descending blade of the propeller has a higher angle of attack. The net result is that more thrust is produced on the right side of the airplane than on the left, causing a turning tendency to the left. Another left-turning tendency is spiraling slipstream. The airflow behind the propeller takes on a spiraling characteristic in the direction of rotation. Since the propeller is rotating clockwise, the slipstream above the fuselage crosses left to right as it moves aft. This pushes the vertical stabilizer to the right, causing the nose of the airplane to yaw to the left. The final left-turning tendency we will cover is gyroscopic precession. The aircraft's propeller exhibits the same characteristics as a gyroscope: rigidity in space and precession. The characteristic that produces a left-turning tendency is precession. This left-turning force occurs only as the nose is pitching down, as when a conventional gear aircraft raises its tailwheel on the takeoff roll. As the nose of the aircraft pitches down, a force is realized at the top of the propeller arc. This results in a force exerted 90 degrees in the direction of the propeller's rotation. This causes the aircraft to yaw to the left. Airplane design has counteracted most of these turning tendencies, especially during cruising flight. However, at high power settings and high angles of attack, such as those used for takeoff and climb-out, you will have to apply right rudder pressure to keep the airplane from turning. Another phenomenon called ground effect is apparent during takeoff as well as landing. Ground effect occurs when the surface interferes with normal airflow patterns, thus causing a reduction in induced drag. During flight at altitude, the downwash created by wingtip vortices causes the average relative wind to be inclined downward. Because lift acts perpendicular to the average relative wind, total lift is inclined aft by the same amount. The component of lift acting in a rearward direction is induced drag. As your airplane descends to within one wingspan of the ground, the wingtip vortices and resulting downwash are deflected horizontally. This in turn moves the average relative wind closer to horizontal, and the total lift vector closer to vertical, thus increasing the vertical component of lift and decreasing induced drag. As a result, the airplane tends to fly longer in ground effect, or float, down the runway. This can be a problem on short runways. Another problem lies on takeoff, where you could lift off in ground effect at a very slow airspeed. If your airplane hasn't accelerated to a safe climb speed before climbing out of ground effect, the airplane could settle back to the runway. Understanding the aerodynamic forces in maneuvering flight provides an important background for learning to fly. In the next section, we will explore the concept of stability and how it affects the way an airplane handles in flight.